Okay, welcome back to our lessons on basic circuit analysis. This is lesson 16, complex numbers and phasors. So first of all, let's remind ourselves what got us here to this complex numbers and phasors. We solved a second order differential equation for this circuit where we had an inductor, L, and a capacitor, C. We set up a second order differential equation, we solved it, and we said that the solution for the voltage across these components was either a cosine, okay, a sine, or a complex exponential. Of the form a e to the j omega 0 or j omega t, right, where j was the square root of minus 1. Right, and in fact, actually when we got here, we kind of ignored case 3 for a while, and we looked at the sine and the cosine. But in fact, these three things are all part of the same family of sinusoids. So if you hear the word sinusoids, these three things apply to that. So you have to, especially if you're an electrical engineering student, you have to get used to the fact that this complex exponential here is a periodic waveform in the same sense that the cosine and the sine are periodic. They're all related, okay? And so that's where we're at today. We're going to try to understand more about this thing here, number 3, complex exponential. All right, so for this lesson, this is more of a math class than anything else. We're going to forget about circuits for right now, and we're just going to talk about a little bit of math. So suppose I had the equation x squared equals 9, right? And you wanted to solve for x. Well, that's simple. You take the square root of both sides, and you get that x is plus or minus 3. Fine. Another way of looking at this, though, is you can make a plot of the left side of the equation, okay, x squared, which is a parabola, of course, and you can plot the right side of the equation, which is 9, a constant. Right, and the solution then is where these two things intersect, of course, at plus 3 and minus 3. All right, now consider the case x squared equals minus 9. Well, if we look at it in the same way, right, as a parabola, here's x squared, but minus 9 is way down here. So where are those two things equal to one another? Well, they're not. They never intersect. So really there's no solution to this. However, if you define j as the square root of minus 1, okay, then you can still quantify this problem in the sense that you can take the square root, both sides, and get x is the square root of plus or minus the square root of negative 9. And you make this definition here, j is the square root of minus 1, then this is plus or minus j times 3. Right, and let's just double check that. If you have the solution j3 squared is j squared times 3 squared, which is negative 9, right, because j squared is minus 1. And negative j3 squared is j squared times negative 3 squared, which is still negative 9. Okay, so both of these solutions apply. So we're going to call j, just a little definition here, j is the imaginary unit. Imaginary unit, and you may have used I in high school or I maybe in some college courses, but we don't use I in electrical engineering because we use I for current. So we're going to stick with j. Now when a number like 3 multiplies j, okay, we're going to put that to the right of j like I have here. It's kind of weird. Okay, it takes some getting used to. But that's what we're going to do. So this signifies to the reader that, oh, this is going to be an imaginary number, right away. So imagine if you had some big expression like x plus 3 cosine t, and then you put the j. So you're reading this and you say, oh, now that's an imaginary number. Let me go back and read it. No, so we usually put the j first. So that signifies right away that this is an imaginary number. All right? Now we use the term imaginary. Unfortunately, it's not a great word, because when we apply it to circuits, there's nothing imaginary that's going on. It's just that the math that uses the imaginary numbers is a nice, convenient tool for us to use. Okay, so we're going to use the word imaginary, and but understand, though, when we do apply it to electrical engineering, there's nothing imaginary going on. The currents and the voltages there in the resistors, they're all physical and real there. So just keep that in mind. Now, one of the important properties of J is that its powers are cyclic. Erase this. Its powers are cyclic. Actually, Stephen Hawking proposed an idea to keep track of time using complex numbers or imaginary numbers, so that we wouldn't have a leap year, believe it or not. So we'll get to that in a second. But let's say I have the number j, right? Just j by itself. And let's say I multiply it by j. Okay? So we've already said that j squared then, right, is minus 1. Okay, so this is minus 1. So if we multiply by j, if we start with j and we multiply it by j, we're at minus 1. So then when we multiply minus 1 by j, we get minus j. Okay, we can't simplify that at all. But then, when we multiply minus j by j, okay, j times j is minus 1, and then we have the minus already, so that actually makes positive 1. And of course, when we multiply positive 1 by j, we get back j. Right? So we have this cyclic nature. So if we go this way, we're multiplying by j. So you see there are really 4 states, and this is why you can keep track of time using complex numbers and imaginary numbers, and you don't need a leap year in that case, because after 4 states it repeats, just like after 4 years you need a leap year currently. Anyway, another property of the imaginary unit is that when you divide by j, right, let's consider 1 over j. Well, I can multiply it by j over j in this case, right, without changing 1 over j. Multiply the numerator and the denominator by the same thing. It's like multiplying by 1. So I've got 1 over j equals, and then in the numerator here I have j, and in the denominator I have j times j, which is minus 1. So this is minus j. So dividing by j, so if I started at 1 and I divide it by j, I end up with minus j. Right? And you can continue on in this fashion, and what you see is you go around this way by dividing. Divide by j. So you see, you can always simplify powers of j, whether they're in the numerator, a positive power, or a denominator, a negative power. You can always simplify them to one of these 4 states. So let me give you an example. Evaluate or simplify, I guess. simplify j to the 7th. Okay, j to the 7th. So this is 1 times j to the 7th, right? So if I start at 1 and I multiply by j, I'm here. That's 1 power. 2 powers, I'm here. 3 powers, 4 powers, 5 powers, 6 powers, 7 powers. So this is equal to minus j. Another way of looking at that is that j to the 7th is equal to j to the 4th times j cubed, right? And j to the 4th is 1 because this can be further broken down into j squared squared. And j squared is minus 1, and minus 1 squared is 1. So this leaves me with j cubed. So j squared, j cubed at minus j. All right, let's try another example. And again, feel free to pause this video. Give yourself some time to think about these questions. Okay, evaluate j to the 113th power. All right, well, j to the 113th can be written as j to the 112th, right, times j to the 1. And I write it like that because 112 is divisible by 4. So j to the 112th then is divisible by 4. So that means we go around the circle an even number of times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So after 112 times, we're back at plus 1. So j to the 112 is 1. So this is just j. All right, let's try one more. Let's try 1 over j to the 5th. All right, so 1 over j to the 5th is equal to 1 over j to the 4th times j. J to the 4th, like we said, is 1. So this is 1 over j, and 1 over j is equal to minus j. All right, so again, you can always simplify powers of j to one of these 4 states, and you're going to put anything that multiplies j, like a constant 5, you put the 5 to the right, and this number is called an imaginary number. Okay. Now, let's look at another example. Let's try to find the solution to x squared minus 2x plus 10 equals 0. Right? Well, to get the solution, I can use the quadratic formula. So we know that x is equal to plus or minus the square root, the opposite of b, so this is plus 2, plus or minus the square root b squared minus 4a times c all over 2a, right? So this is 2 plus or minus the square root. I've got 4 minus 40. There, so x is equal to 2 plus or minus the square root of minus 36 over 2. So what's the square root of minus 36? yeah, it's j times 6 over 2. The 2's cancel, so I'm left with 1 plus or minus j3. There are my two solutions. Okay, now this, first of all, each solution, so x is 1 plus j3, or x is 1 minus j3. Each solution here is called a complex number. And a complex number has a real part, okay, that's the 1 in this case, and it has an imaginary part, the plus 3j3 here and the minus j3 here. So this guy is the real part, okay, real part, and this guy is the imaginary part. Okay, so in general, now, a complex number has a real part and an imaginary part. Okay, now the number 1 plus j3, this cannot be combined or broken down even further. It can't. You cannot add 1 with j3. That is, you cannot add a real number with an imaginary number. It makes no sense to do that. In this regard, then, this number, this complex number, can be thought of as a two-dimensional vector, right? So think about physics and what you know from vectors. If you walked, 3 miles east, and then you walked 4 miles north, okay, you could represent that as 3. In physics you use, I guess we'll use, physics you use I with a caret over it maybe, and 4j, not to be confused with the j we're talking about here. I think this is what you use in physics, right? But you could not combine the 3 and the 4 and say you had a vector of 7. No, it doesn't work like that, right? Actually, you're 5 units away at that point, right? So you cannot combine east in this case with north, and same thing here with the complex number. You cannot combine the real part with the imaginary part. So again, in that case, it looks like a vector. So we'll consider it as that exactly. So we'll oftentimes use an axes or a coordinate system with the imaginary axis being the vertical axis and the real axis being the horizontal. So we can plot, for example, this complex number, right? Go over 1 unit to the right and up. The j means, this is a positive, and then this is the direction j. J means to go up the imaginary axis. So go up 3 units. And so our complex number looks like this. Right? That's a vector. Call this x1. Right? So here's x1. Right? And our other solution is 1 minus j3. So we can plot that as well. That would go 1 unit to the right and down 3 units. Okay, I call that x2. Okay, so there are our complex numbers in this complex plane. So the imaginary versus the real, that's called the complex plane. All right. Now something interesting happens when you multiply by j. So we'll consider again x1 here. I'll draw this in green. Consider a new complex number, x3, and we'll say it's j times x1. Okay, so we're taking a complex number here, and we're multiplying it by j. So let's carry out that multiplication. When I distribute the j, I get j times 1 is j, and then I get j times j3. So that's actually minus 3. So when I do that multiplication, I get minus 3 as the real part, plus j is the imaginary part. So let me plot that. So I go to the left 3 units and up 1 unit. If I've drawn my plane correctly, something nice happens. I get a right angle here. Okay? I get a right angle. That is to say, multiplying by j rotates the complex number by pi over 2 radians. Okay, 90 degrees. Let's see why that is. Actually, we can prove it. Okay, so I'm going to use z. Z is common for complex numbers. So in general, if z is a complex number, it can be written as a plus j times b. So some real part a and some imaginary part b. And if I have another complex number, z2, which is z1 times j, then this is minus b plus j times a. Okay, now we're reaching here, but follow this. If we write these as vectors, so I've got a and I've got b, and I do the dot product of those two vectors. So here my real part is minus b, here the imaginary part is a. If I take their dot product, this gives me minus ab plus ab, which is 0, right? And this turns out to be, remember the dot product is the magnitude of the vector z1 times the magnitude of the vector z2 times the cosine of the angle between them. So the magnitude of this vector is not 0, right? The magnitude of this vector is not 0. So what has to be 0 here is the cosine of theta. And if the cosine of theta is going to be 0, then theta is pi over 2 radians. So therefore, we've just proven this idea. All right, well, again from physics, if we're considering the complex numbers to be vectors, you should know that you can represent vectors in a couple different ways. Representations, we'll call it representations. All right, the first way you can represent a complex number is exactly how we've been representing it, a plus jb. So this is the real part a and the imaginary part b, and we'll call this rectangular form. Rectangular form. Sometimes this is called Cartesian form. This is how far over you go one way, right, on the horizontal axis, and then how far over you go up and down. So that's rectangle. It forms a rectangle. You go to the right or to the left so much, and you go up or down so much. So you're forming a rectangle, rectangular form, a Cartesian form. But you know that that's not the only way you can express a vector, right? You can write it in polar form by giving me the magnitude of the vector, okay, and the angle or the phase of the vector. So this also uniquely specifies a vector in the complex plane. This is polar form. And if you're given rectangular form, how do you get r and theta? Well, r is the magnitude of the vector. That's the square root of a squared plus b squared. Now be careful here. We're leaving off j, right? So let me draw your attention to this because this is a common mistake. Right here, the b squared, leave off the j. If you put the j in there, then you're going to square the j, and this plus is going to become a minus. No, don't do that. Leave off the j. The j is the direction. Okay, the east-north example, you don't put 3e squared and 4n squared for north. You leave off the direction. So you're going to do the same thing here. You're going to leave off the j when you calculate the magnitude. Right? And also you should know that theta is the inverse tangent of b over a. Alright, so if you're given rectangular form, this is how you get polar form. And if you're given polar form and you want rectangular form, so you know that the a, or how far over you go in the horizontal direction, is r cosine theta, right? And how far up and down you go, b, is r sine theta. All right, and another way we're going to express our complex numbers, and it might seem redundant at first, but it's handy mathematically. We're going to use r and theta again, and we're going to call it r e to the j theta. And this is exponential form. And this might seem a little weird at first, but you'll see why we're going to do this in a little bit. This is exponential form, okay, and it's our third way of representing our complex number. And also, in this form, this is called a phasor. So this is the second part of the title here, phasor. Okay, so let's look at an example. Okay, just a quick example. Express 2 plus j2 in polar form and exponential. Alright? So I've got rectangular form a and b. A is 2, b is 2. So let me calculate r. R is the square root of 2 squared plus 2 squared. Right? So that's 4 and 4, that's 8, that's 2 root 2. Theta is the inverse tangent of 2 over 2. That's pi over 4 radians. So in polar form, this would be 2 root 2 angle pi over 4. And in exponential form, the phasor here is 2 root 2 e to the j pi over 4. All right. Still sticking with what you know about vectors, particularly from physics. Again, this is the imaginary axis, this is the real axis. Suppose we had two complex numbers, z1. Okay, I'll draw it. Let's say z1 is, well, we'll just say a1 plus jb1. And suppose our second complex number, z2, is a2 plus jb2. Right? And suppose we wanted to add them together. Right? So maybe here's what z1 looks like. And you know that you add vectors tip to tail. Maybe this is what z2 looks like. So we're going to take z1, and then on top of it we're going to put z2, and the resulting vector, this guy, is z1 plus z2. Right? So if z1, let me do this in a different color, if z1 went over a1, right, and then on top of that z2 goes over another a2, right? So actually, so this distance here is a2, and this distance is a1. Well, our resulting vector is how far? a1 plus a2, right? And same thing in the other direction. If z1 went this high, this is b1, right? And then z2 went another b2, how tall is our resulting vector? That's b1 plus b2. And so our resulting vector, z1 plus z2, is a1 has a real part, a1 plus a2, and has an imaginary part, b1 plus b2. So the takeaway here is that addition and subtraction, because subtraction is just if we were subtracting z2 from z1, we would just turn z2 around, right, and make it point the other way. Addition and subtraction are best performed in rectangular form. This is because, again, their real parts add and their imaginary parts add. All right, let's look at an example. Okay, add z1 equals e to the j pi over 4 with z2 equals 2e to the j pi over 2. All right, so how are you going to do that? Well, you're not going to do this. You're not going to say, oh, well, the answer is this. No, don't do that. What you're going to do is first convert each one of these to rectangular form. All right, so z1 here has a magnitude. You know, the magnitude is the number out in front in exponential form. So this is 1, and a phase pi over 4. So the magnitude, so the x-coordinate is a equals 1 times the cosine of pi over 4, and the imaginary coordinate is 1 times the sine of pi over 4. So the cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is also root 2 over 2. So z1 can be written as root 2 over 2 plus j root 2 over 2. Same thing with z2 here. We'll convert it to rectangular form. So a here is 2 cosine of pi over 2. So cosine of pi over 2 is 0. And b is 2 sine of pi over 2. Sine of pi over 2 is 1. And so this is 2. Alright, so now z2 in rectangular form is simply 0 plus j2, or just j2. So now when I do the addition, z1 plus z2, I have a real part, square root of 2 over 2, and an imaginary part, square root of 2 over 2 plus 2. So I can get a common denominator if I like. 2 is 4 over 2, so this is 4 plus root 2 over 2. Alright, there's our answer. And if you want, you can convert this back to exponential form by getting the phase and the magnitude. Alright, so let's move to multiplication and division then. So if I had two numbers, okay, r1 e to the j theta 1 and r2 e to the j theta 2, so now you're going to start to see why we express them in terms of exponentials. If I multiplied them, let's say z equals z1 times z2. Notice if I multiply them, I get r1, r2, e to the, so what happens with the powers when I multiply the same base? The powers add, right? So this guy now looks like, we'll call this z3. Z3 is the resulting. So this guy looks like another magnitude, right, r3, and this thing looks like another phase, theta 3. In fact, it is, right? It's in this form. So we conclude that the magnitudes, when you perform a multiplication, the magnitudes multiply and the phases add. So multiplication is best done, and division, are best performed in polar or exponential forms. Right, a division, if you wanted to look at division, let's take a look. Z4, let's say, is Z1 over Z2. How would that division work? Well, we would take R1 e to the j theta 1 divided by R2 e to the j theta 2. Alright, so we've got R1 over R2, and what happens to the powers here? Same base, subtract. So you see in division, the magnitudes divide, the angles subtract. It's very simple in exponential form. So let me give you an example, a concrete example. Let's let z1 equal the square root of 2 over 2 plus j square root of 2 over 2. And let's let z2 equal the square root of 3 over 2 plus j times 1/2. Find z1 times z2 and z1 divided by z2. Okay, so I'm going to let z1 equal this guy, z2 equal this guy, and we're going to find the product and the quotient. All right, so z1 times z2, well, we've got multiplication, we've got division. All right, so first thing we should do is put these guys in exponential form or polar form. That is, find the magnitude and find the phase. So the magnitude of our first complex number is what? Can you just tell me quickly? It's 1, because this point lies on the unit circle, square root of 2 over 2, comma square root of 2 over 2. So its magnitude is 1. And what is its phase? Well, that's pi over 4. So if you didn't believe me, you could do the square root of this squared plus this squared, and you get 1. And then for the angle, you could do the inverse tangent of this square root of 2 over 2 divided by the square root of 2 over 2. Now, for z2, this point also lies on the unit circle. So its magnitude is 1, and its angle, so you go over square root of 3 over 2 and up 1/2, you're at an angle pi over 6. Right. Okay, so then z1, z2 multiplication is e to the j pi over 4 times e to the j pi over 6. Okay, so we can get a common denominator there of 12. This is 3 pi over 12, and this is 2 pi over 12. So that makes 5 pi over 12. And z1 over z2, okay, that's e to the j pi over 4 divided by e to the j pi over 6. Again, so that's 3 pi over 12 minus 2 pi over 12. So this is e to the j pi over 12. All right. Next, in our complex number primer, is the so-called complex conjugate. Complex conjugate. And I'm moving quickly here because most of this should be a review for you. The complex conjugate, if we have a complex number, c equals a plus jb, the complex conjugate is denoted by this star, asterisk. And you've heard conjugate before, I'm sure. For example, if you had a trig class in high school, one of the methods you had to proving trig identities was to take the conjugate. Let's say you had something like this, to multiply by the conjugate of the denominator. Right? This is, and the conjugate of the denominator, you change the minus to a plus. Something like this. Does this look familiar at all? Where you change the minus to a plus? I don't know. I did that in high school. I don't know if you did. But the idea is that the conjugate was you had something plus minus something else, and the conjugate was to change the minus to a plus and the plus to a minus. So a complex conjugate is we're going to change the imaginary part to a minus. Okay. Geometrically, if you had a complex number, say here's z, here's our complex number z. If I change the imaginary part to minus, what would z conjugate look like in this plane? Well, I go over the same amount. A has not changed, but instead of going up by b, I go down by b. So geometrically, the complex conjugate is a reflection over the real axis. It's a reflection over the real axis. And something nice happens when we multiply z times z conjugate. And this is really why conjugation is important to complex numbers. It's because something magical, something beautiful happens when we do this multiplication. Notice we have a plus jb times a minus jb. And this is an instance where I can carry out the multiplication in rectangular form because we have something that simplifies. So if I FOIL this out, I get a times a, and that's a squared. A times minus jb, that's minus jab. Then the inside term gives me plus jab. And then the outside terms, I have jb times minus jb. Well, j squared is minus 1, so this makes jb squared. So look at the imaginary parts cancel, and I'm left with a purely real number, right? A is real, B is real. This is a purely real number. All the j's are gone. Further, what real number am I left with? This is a special number. Of course, this is the magnitude of z squared. Right? So we conclude the magnitude of z, right, which was the square root of a squared plus b squared, can also be written as the square root of z times z conjugate. This is a really nice property. All right, now we did the multiplication in rectangular form. Let's suppose we write it in exponential form, r e to the j theta. So we said in rectangular form that when you take the conjugate, you change j to a minus j, and that's a reflection over the axis. So if this is our original angle, theta, what can you say about our conjugate angle? It's minus theta. So we can alternatively express z times z conjugate in exponential form, r e to the j theta times r e to the minus j theta. And notice what happens again, we get r times r is r squared, e to the j theta times e to the minus j theta is e to the 0, which is 1. So again, we conclude, look at, we're left with the magnitude squared. It's exactly what we got in this case. Again, so the magnitude of z, which is r, right, this is what we're calling r, is the square root of z times z conjugate. All right, so let's look at a concrete example. Find the magnitude of 3 plus j4 by, we're going to use the Pythagorean theorem, and we're going to use the complex conjugate. Okay, and of course both of those we should get the same answer. So first for A, Pythagorean theorem, so I go over 3 and up 4. So r is equal to the square root of 3 squared plus 4 squared, right? That's 5. B, r is equal to the square root of 3 plus j4 times 3 minus j4, the conjugate. So if I do this, again, I FOIL this out. So 3 times 3 is 9. I know the imaginary parts will cancel, so the cross terms are the imaginary parts. The last terms in each case, I have j4 times minus j4, which makes plus 16. So that's 25. The square root of 25 is 5. All right. So now I want to come around full circle. Remember what got us here. And that was sinusoids. A sinusoid is a cosine, a sine, or a complex exponential. All right, well, let's prove it now. Let's prove that these are all part of the same family. Now we're going to dig down real deep in our mathematics knowledge. Remember that e to the x has a Taylor series expansion. That means it can be written as a sum of polynomials like this. 1 plus x over 1 factorial plus x squared over 2 factorial plus x3 over 3 factorial, and so on. Cosine, again, we're digging down deep here in our knowledge, also has a Taylor series expansion. Cosine's an even function, so we keep the even terms, and it also has an alternating sign, S-I-G-N, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, and so on. Okay, sine has a Taylor series expansion as well. Sine is an odd function, and its Taylor series expansion is x over 1 factorial minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, and so on. So we'll just keep that in mind for right now. But let's look at the exponential, because that's kind of what brought us here. Well, instead of e to the x, right, I saw that I had something like this, e to the j omega. And we'll just t, but let's call it e to the j theta. The fact is that we had an imaginary power, right? E to the j times something. All right, so let me, using the Taylor series expansion, expand on e to the j theta. So this is 1 plus. So everywhere I see an x here, I'm going to plug in j theta. So this is j theta over 1 factorial plus j theta over 2 factorial plus j theta cubed over 3 factorial plus j theta to the 4 over 4 factorial. I'm going to carry out a few more terms because we're going to need them so that we can get the general idea. All right, and this keeps going. Now, we'll leave the first two terms alone. What do I get if I distribute the square into the parentheses? J squared is what? minus 1, and then I'll have theta squared. If I distribute the cube into the parentheses, remember this thing? It's minus j. So each time I multiply by j, I go around this thing, I have this cyclic nature, right? So j cubed is 1, 2, 3 minus j. This is minus j theta cubed over 3 factorial. J to the 4th, 1, 2, 3, 4, I'm back at 1. So this is just theta to the 4 over 4 factorial. J to the 5, well, that's j times theta to the 5th over 5 factorial. J to the 6th is minus 1. Right? 1, 2, 3, 4, 5, 6, minus 1. And another j, this the next term, is minus j again. Minus j, theta to the 7th over 7 factorial. The next term is going to be plus, and so on. Alright, so let me combine all the real parts here. So I've got 1, and then I've got a minus theta squared over 2 factorial, and a plus theta to the 4th over 4 factorial, and a minus theta to the 6th over 6 factorial, and I keep going on like this. Let me combine the imaginary parts and factor out the j. So I've got theta over 1 factorial minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus, and so on. Alright, so what do I have here in the first set of parentheses? Yeah, I've got the cosine of theta. What do I have here in the second set of parentheses? Sine of theta, right? And let me remind you again, this is e to the j theta. And so e to the j theta is nothing but cosine of theta plus j sine of theta. In other words, a complex exponential is a sum of two sinusoids that are 90 degrees out of phase. This is called Eulers equation or Eulers equation or Eulers relation. And it's all due to the fact that the cyclic nature, right, gave us the changing signs, SIGN, changing signs in these terms, plus, minus, plus, minus. If this was not a complex power, if the j was not there, we would not have these alternating signs in the exponential's Taylor series expansion, and we would not have a cosine or a sinusoid. So it's that complex exponential that gives us the sine and the cosine. Now, just a point here. Something nice happens when you plug in theta equals pi. You get e to the j pi equals cosine of pi, which is 0, right? Plus cosine of pi is minus 1, plus j sine of pi is 0. And if I add the 1 over e to the j pi plus 1 equals 0. This is a special form of Eulers relation. Okay, this is called Eulers identity. And this is what's known as the most beautiful equation in all of math and science history. Anyway, right, people vote on this stuff. What's the most beautiful equation in math and science history? This one usually wins. This is what tattoos are made of, right? So let's just give this a few thoughts here. You've got E, which is an irrational number. It's like 2.71 something. It goes on forever without repetition. And it's the fundamental constant for calculus. Pi is also an irrational number, 3.14 something, goes on forever without repetition. It's the fundamental constant for geometry. And before Euler, these fundamental constants were thought to be unrelated to one another. So here you've got E, this number that does not repeat. Raise that to a seemingly unrelated irrational number, and oh yeah, multiply that number by the imaginary unit. Right? Take that and add 1, which is a perfectly rational, real number, and what do you get? You get nothing. How beautiful.